It's my honor today to introduce you the speaker, Professor Bhuvnesh Jain from UPenn, who is an expert on cosmology, weak gravitational lensing, and machine learning applications in astrophysics. He is the co-director of Center for Particle Cosmology and the Data-Driven Discovery Initiative at UPenn. He did his bachelor here at Princeton, and then get his PhD at MIT with Professor Edmond Petriner and Alan Booth on the theory of large structures. Booth is one of the pioneers of using weak gravitational lensing for precision cosmology. His early work laid much of the theoretical groundwork for weak lensing, including using calculating the power spectrum in nonlinear dream, high-order statistics, weak lensing tomography, and joint lensing and galaxy survey and galaxy clustering, which had become standard tools now in the era of large surveys. And equally important, he is heavily involved in the major surveys, including DES, Rubin LSSD, Euclid, and Roman. He coordinated the DES weak lensing working group, co-chaired the LSSD weak lensing science collaboration, and served as the first spokesperson of the LSSD dark energy science collaboration. And he also made lots of contributions in other aspects of cosmology, as well as machine learning in astrophysics. So the list goes on, so I won't mention all of them. So I'll just leave the time to Booth, and today he'll tell us about weak lensing and cosmology. So please join me and welcome Booth.
Thank you, Bhuvnesh. Great to be here. Also a difficult talk to prepare because some of you who work in weak lensing work on exactly this stuff. And of course, many of you don't. So it's going to have some uneven level of generality. One of you is going to be surprised to see a figure that you may have even forgotten. That's in my talk. So I apologize for, sorry. Is there a pointer? Does this serve as a pointer? Oh, yes, okay, great. So I just have some partial references here to analytical methods, three-point functions, wavelets, and a slightly separate topic, mass mapping with diffusion models. And I have honestly not been able to keep track with the archive in many, many months. And so I apologize for almost a complete absence of citations other than these papers. The work has been mostly done by my students and postdocs, Rafael Gomez, Minsu Park, Kunhao Zhang, undergrad Michael Jacob, and postdocs Sonal Sugiyama, Supranta Borua. Marco was in Chicago until his visa status got messed up. And so he moved to Barcelona only a few months earlier than planned. He has a nice position there. And of course, all the data that I'm going to show is mostly from the dark energy survey. All right, that's my outline. Mainly, I'll talk about the cosmic puzzles as motivation for weak lensing. And the heart of my talk is about three-point correlations. And then I'll show some results on mass mapping with diffusion models. So I know you've heard about the SA tension, which is that the growth of structure in the universe appears to be slower than predicted. By predicted, I mean take the baseline lambda CDM model and extrapolate from the CMB to the late-time universe. This is by no means a statistically significant problem. It shows up in some lensing and galaxy clustering measurements, and it's below 2 sigma, even where it does show up, or at most 2 sigma. And CMB lensing, which probes some of the same redshift regime, and at least the latest DESI power spectra do not show any issues. And just last week, Biwe Urosh and co. had a paper that appears not to show any issues. There's also the H0 tension that I won't talk about. I'll briefly talk about the evolving dark energy tension. As you know, the DESI survey published these beautiful BAO measurements, and this is their W of Z reconstruction, the green band is the model fit to the W0 WA parameter space, and the points show that that fit is not too misleading. In other words, there is a phantom crossing, there's time evolution at the 2 to 3 sigma level if you combine BAO with CMB. Actually, this includes supernovae, sorry. There's the reconstruction of the distance modulus from supernovae, which shows that a lot of the signal hinges on this point below 0.1 that was discussed in the DESI papers and by various others. So we were interested to see if weak lensing has anything to contribute. We found that we have to wait for LSST, but not too long. LSST year 1 will become comparable to the current supernovae. So what Kunhao did is he extracted the geometric part of weak lensing. You do this parameter splitting, and then lensing mixes geometry and growth. So if you extract the geometry, then you can combine it with other geometric probes. So this plot, if you've not seen it, tells us that an Astro 1 level question is actually something none of us understands, which is what is the mass density of the universe? We all agree it's baryons and dark matter, but apparently we really don't know what dark matter is, because at least within LCDM, different probes, BAO, CMB, supernovae, large-scale structure, give different answers. So this is the simplest kind of intuitive way to understand the theoretical origin of this evolving dark energy, that what we think of as a single component dark matter that is isolated from other components is in fact interacting with dark energy or decaying into radiation or doing something, so that when we do a fit, assuming rho matter goes like 1 over a cubed, we're actually making a mistake. And if we've had the right theory model, all these curves would fit much better together. So along with looking at the weak lensing contribution, we looked at the supernovae and found that in this plot, you can see quite dramatically the concerns that have been raised. This is the supernova result, and this is what happens if you remove a small fraction of supernovae, but an important small fraction, namely the ones below 0.1. So they are known to have some concerns due to calibration being very inhomogeneous. And of course, the supernova community has done their best and is continuing to work hard on it. But that does raise the question that other than BAO and CMB, what can be used to truly probe this question?
Are these the DES supernovae or?
Sorry, yes. We have only, yes. So there's already the issue that the 3 premier supernova samples have 1-ish sigma tensions between them. But setting that aside and using the most discrepant, the most indicative of evolving dark energy, we find this more than 1 sigma shift. Any other questions? So if you set those aside, then CMB, BAO pretty much by themselves, but if you toss in galaxy lensing of 3x2, you still get a 3 sigma tension with LCD. And there's, as you may know, there's a ton of other work examining different parts of this. Something that I found encouraging is that if you take LSST year 1 weak lensing, then its constraining power is quite a bit bigger than at least current DES and will be bigger than the complete DES. And so you would get this orange curve. If you say that LSST is in the southern hemisphere, we won't be able to calibrate photoz's as well. And so we're just going to use the photo Z priors at the level of DES, and that's what we call conservative. So you can see that at least it'll be comparable in precision to current supernovae. So it'll be great to have that probe. We'll have other probes, RSD, and maybe others. So the story is, of course, going to be fascinating space to follow. And I'm eager to see the DESI full shape analysis. All right, I'm going to switch to the main part of my talk. This is the DES year 3 mass map showing dark matter superstructures and cosmic voids. There's beautiful mass maps from CMB lensing that cover almost the whole sky. So this is an exciting time to be doing lensing. And our year 6 analysis is pretty imminent. Alex Aman is one of the leaders, and you can look forward to some exciting papers in the coming months. Just to set the stage a little bit for the essay tension, there's attempts to reconstruct the 3D power spectrum. This is still following the same procedure that Matthias showed us a couple of decades ago with Max. And so this is the ACT lensing survey, ACT lensing measurement converted to 3D DES. The bins become very wide because you're going from an angular measurement to a 3D. But you get within some cosmological framework, you're not doing parameter fitting. You're reconstructing the 3D power spectrum at redshift 0. And so, these are small effects, but we find that DES, the published results, need a lower amplitude in addition to a modest scale dependence. But when you combine with ACT, then you see some clear scale dependent suppression. Notice we're going to very high K here. So this is some mix of SA and possible baryonic suppression. There's a really nice paper by Preston et al. From Peyton Hall, where they explore something similar, namely, can this be explained by baryonic feedback or ultralight axion model? And it's very hard to disentangle, but we know that baryonic feedback is real, and so is the likely explanation for this still low statistical significance suppression. All right, before I show you other results, the sources of uncertainty in weak lensing, there's 3 big ones: baryonic feedback, intrinsic alignments, and photometric redshifts. These are called astrophysical, and this is, I guess also astrophysical measurement. Various other sources of uncertainty, namely measuring the shapes of galaxies in an unbiased way and correcting for the point spread function, are currently quite a bit smaller than statistical errors, which is a tribute to the great work that the weak lensing shear measurement folks have done. And there's many other sources of uncertainty that are going to become relevant for stage 4 surveys. But these are the 3 that I will address in today's talk. And there's some great work by folks right here, Vive Urosh and their group, and Alex and her group, that I'll allude to. But of course, I'll let them give you talks about their work. But these 3 surveys, Euclid is underway, LSST is to start in a few months. Roman is scheduled to fly in 10-ish months. So, and as you know, space missions start giving you survey quality data within months. So they're all going to be happening at the same time within 2 years. So it's very exciting. And my guess is that we will very likely be in the systematics dominated era for sure, multiple systematics within 1 year of these surveys. I'm going to show you higher order correlations. Let me just jump to 3-point functions. So, so when you measure sheer 2-point functions, you're measuring the shapes of galaxies separated by some distance on the sky. When you measure 3-point functions, you're multiplying the shear at the vertices of a triangle. And there's 2 components. So you get 2 times 2 times 8 3-point functions. And 4 of them carry cosmological signal. The other 4 are useful for sanity checks. And so some of us had worked out a while ago what the signal looks like as a function of opening angle of the triangle. Unlike a 2-point function, you can see it's very rich. It has 0 crossings, and that gives it a lot of power as one part of the analysis. The black points were halo model predictions, were simulations, sorry, and the solid curve was our halo model prediction. So we had a great handle on the theory a long time ago. I'll talk a little more about this shape in a second, but it took us more than 20 years to make a good measurement that's good enough for cosmology, that's good enough to show this characteristic shape dependence. So this is DES year 3 in the points, and the band is from simulations with all mocks that are designed to match the redshift distribution and so on of DES. So this is really nice. This is gravity. And so you can take a point spread function pattern and you'll find some completely other 3-point function. So it's definitely, this is a cumulative signal to noise of 15 or so. For the 2-point function, it's 50. So it's lower signal to noise, but there's things you can do with a 3-point function you absolutely cannot do with a 2-point function. Anybody remember this plot? This is from Matthias and Roman Scott-Chimaro. They chose the wrong angle, so their thing goes the other way. Their opening angle is not the one between the sides of the triangle, but 180 minus that. But you can see this shape is the same as this shape. There's a 0 crossing. And what's nice about this is that this is just a single isothermal sphere. You're moving triangles around and averaging them over the field of view. In other words, this doesn't take cosmological large-scale structure, blah, blah, blah. It's just kind of one halo dominated, and it's gravity and the nature of a spin-2 field. So after my students had worked on this for a very long time, I asked them to read this paper and please explain it to the whole group on the blackboard. And it wasn't easy because a lot of people don't think about physical intuition as carefully these days with so much simulations and computing and machine learning. But it's very instructive. So we then did a whole cosmology analysis with lots of machine learning elements, data compression, and systematics analysis. I'll just show you a couple of bottom lines before we discuss the analysis details. This is with simulations, where we found that in the S8 omega matter parameter space, you gain almost exactly a factor of 2, which was quite surprising to me. I had thought that one needs more powerful higher order statistics. See how Chang was at IIS, and he had talked about the power of wavelets and scattering transforms. But in fact, the 3-point function, if you actually use all the triangles, is pretty powerful. No surprise to those of you who work with redshift space bispectra. But in the weak lensing community, it had fallen a little out of favor. So SA is the amplitude of mass fluctuations related to sigma 8. It's the thing lensing is most sensitive to. So we then did the same analysis with DSEO3 data. And again, this is the 2-point function. This is the 3-point function by itself. You can see that there's some degeneracy breaking. And this is the same slightly bigger factor gain and precision.
So I guess if in the previous slide, you argued that this, just plopping down isothermal spheres in a halo model type approach captures a lot of the qualitative features of the signal that you said were important.
Yeah.
But the isothermal sphere profile knows nothing about cosmology.
Right.
And so where exactly is the constraining power coming from? Is it just the fact that you're measuring somehow halo abundances in this new weighted way by measuring this one halo regime? I guess.
So you could, I mean, the very short answer is that the amplitude is cosmology dependent. It's, sensitive to SA to omega matter in a slightly different combination with 2-point function. It's the shape that is predicted just by gravity.
So the information is not necessarily in the shape, the cosmological information.
Yes. There's very limited. I mean, if you just take a point mass and you sit it here, you'll get that peak, the maximum here. And then if you just start opening this angle around, then you'll find that, this produces a tangential pattern. And if you start moving the angle around, you'll see that one of them's flip sign, and so it has to go negative. So you can just get the shape just with anything, as long as it's gravity producing tangential shear patterns. It's very simple. But of course, the location of the zero crossing and the details depend on Washington. But it's mainly the amplitude. And of course, we also use all the other 3-point functions as well.
Sorry, question. If you were to use just a pure, halo model plus isothermal or NFW profiles, would the model fit? Does the data discriminate between the full simulation-based inclusion and just that kind of simple toy model?
You could do very well with the halo model, although I don't know. I certainly haven't tried that in almost 2 decades, so I can't answer that with any precision. But there's this bi-halo fit.
Yeah.
Which is halo model inspired. And so, yes, so it's got a lot of free parameters. So it's basically a simulation fit, but very loosely. Gravity is non-local. So the one halo regime extends quite far for the 3-point function, but you do need 2 halo contributions. Other questions? Right, so you can see that we find some modest 2 sigma tension with the CMB. And so this is the 3-point function combined with basically the published 2-point analyses that were presented in Alex Amon and Lucas Echo et al.'s papers, just with one minor correction. But of course, there's many other analyses of that data that do interesting things and find different things. Alex's group has some of the best ones, but this was what we found with the 3-point function. I won't talk about all these tricks that we used, but this paper, I think, is particularly useful for anybody looking at data compression. I know in the RSD community, you use in DESI some kind of template fits to compress the data, but if you wanted to use a more kind of objective way, then we've made some, I think, significant advances, happily in the direction of simplicity. So linear methods to compress data, generally speaking, outperform neural networks unless you have infinite compute and simulations. One nice thing with the 3-point function is that we are able to get some self-calibration of the photo Z's. So it's not as beautiful. I'm going to show your HSC results as actually doing it right with a spectroscopic sample, but we don't have a spectroscopic sample yet that can let us calibrate photo Z's for DES. So it's nice to be able to do independent check. So if you look at this bin, delta Z4, with S8, this panel, then green is the fiducial analysis. Red is what happens if you drop the prior on the 4th redshift bin. So you can see S8 is degraded, but you have almost very little self-calibration. If you add the 3-point function, then S8 is still degraded, but you're able to self-calibrate the photo Z. And in the S8 omega matter plane, you see the red contours are only modestly bigger than the green ones.
Sorry, what does this mean, the 3rd and 4th redshift bins?
Sorry?
What does it mean, 3rd and 4th redshift?
Sorry, yes. I should have explained that. So, you have the observer. So in these recleansing measurements, we break the sample into 4 bins currently. And so this is the farthest redshift bin.
And I mean, how are the boundaries chosen?
That's
Is this like a standard in the field, or is
it's
this physical?
specific to every survey. Yeah, you kind of know what your highest redshift galaxies are, and then you try to break them into roughly 4 equally spaced bins. But then it depends a lot on the calibration sample and so on. So in fact, the redshift distributions look like this. I'm just drawing this boundary. So in fact, they overlap and so on. So that story is very complicated, but certainly for DES and generally, it's the highest redshift bin for which our estimate of the redshift distribution is least certain. Generally speaking, we've also found some issues with other redshift bins because of how spectral features transition filters. But it was nice to be able to calibrate only one of them at a time. So the thing is that there's 4 bins and you measure cross bin triangles. So you have 20 bin combinations. And that's what gives you the self-calibration capability. So you leave 1 out and you still have enough. But if you take 2 out, then you lose almost all calibration ability. So
I was also going to ask, so the delta Z4 you're talking about here is a shift in mean redshift,
that's right.
mean true redshift of that nominal 4th redshift bin.
Correct.
And there's also, do you guys have a stretch parameter, and have you looked at the impact of being even more specific about what that shape really might be?
We're not using a stress parameter at current
So
precision.
the whole bin correction is defined by a shift in mean.
Yes.
But we did test it for Y3 and it didn't matter.
The stress parameter. Yeah.
Like the whole shape, the full shape of the distribution, and it doesn't matter. Yeah, I'll be able to. But I think this is holding us for now.
I mean, I'm sure it was a good test, but if I added 50% of the objects at redshift of 3, it would matter.
Right.
So there's something that could happen with the shape that would matter. It just wasn't within plausibility, I guess.
Yeah.
Yeah.
Fair.
Yes, as Eric's pointing out, we're just looking at deviations about the estimated mean of that bin. And so this is the level of self-calibration as, 0.02, 0.03.
Is there something a bit funny? Or I'm curious, why is the red contour above the delta Z? Like, is there like a bias that I'm not?
It's a 1 sigma shift. Yes.
Oh, okay.
Good point. Yes.
Yeah.
So in fact, the results I showed, the SA tension goes up if we use the self-calibration.
I see. Okay.
Yeah, we just treat it as a check.
Yeah.
Yeah, it is a shift, you're right. But I mean, you can see in S8, you can see, it's like hard to see, but
Yeah.
it's a 1 sigma shift in the delta, in the redshift
Yeah.
of one bin, which leads
Right.
to a 0.2 sigma, 0.3 sigma shift in S8.
Right.
I understand this figure as the blue and the green just show that you're prior dominated if you assume a strong like Gaussian prior center at 0, and then if you don't assume a Gaussian prior, you get the red curve, which is the information coming from the 3 point.
The blue,
Because the blue and the green delta Z4 look the same, right? Like the rightmost posterior.
here,
Yeah. So is that just the prior that was actually baked into the fiducial analysis for what the shapes would be?
right, yes, yes. That's the estimated photo Z, yes. Sorry, I didn't present this very clearly. All right, my worries and hopes. My worries are about myself. My hopes are come from the rest of you. We use a simple model for intrinsic alignments, the simplest out there, NLA, too simple. And we have kind of a cop-out explanation that we and other analyses don't find a signal of intrinsic alignments, but that's certainly not adequate justification. So our model has two parameters. In our even in our baseline 2-point function analysis, we also test with TAT, but in practice, we didn't figure out a TAT implementation for the 3-point function. But there are EFT-based models that Nick and others are working on that are far more sophisticated, difficult to incorporate into a cosmology machinery. I love Alex's approach of finding a galaxy sample that is very, very likely to have much lower intrinsic alignments. So that's pretty powerful. It's still a lot of work because you got to estimate its redshift distribution, and its shear calibrations and so on, but well worth it. So this story is going to play out. There's still limited, there's some, but limited hope that we'll be able to directly measure them because spectroscopic surveys don't get at most of the galaxies used for the shapes that we measure. But there's a lot of advances, and we'll see if we can mitigate IA without losing significant constraining power. Certainly for stage 3 surveys, I think I'm hopeful thanks to the work of some of you. Baryonic feedback is a big topic that, again, members of the audience have worked on much more than I have. And there's a lot of interesting results. Joint analysis of lensing and thermal SZ and kinetic SZ, cross correlations of SZ with shear, kinetic SZ around galaxies, clusters, X-ray and SZ. And the emerging picture is that we did not get lucky with baryonic feedback. Feedback is fairly strong. The story is, coming together, but it is here. There's hope from data. Currently, lensing is sensitive to some range of halo masses, and we are measuring SZ from some part of that range currently. When we can match those ranges completely, we should have a great deal of confidence in being able to fit for baryonic feedback from the data. And of course, there's huge work in hydro simulations. Photo Z, Dr. Biway. And you'll see that this problem has been solved by Biway, Orosh, and their groups for HSC. But for kids in DES, which are in the South, there's ongoing work that will help some. When we talk about things like EFT-based models for intrinsic alignments, I wake up in the middle of the night worrying about projection effects in parameter space. And that's why, I'm really glad that we'll get empirical constraints on baryonic feedback, because so far we have not seen a very clean story of coming up with a complicated model for systematics that satisfies everybody, but does not lead to confusion in parameter inference. For DESI, you see this with your bias model. It's just really tough when you have non-trivial parameters of order 10 that you're fitting for. And in case you're a grad student thinking about stage 4 surveys, there's a whole new set of systematics you can work on, which are definitely gonna be relevant. So when I look at the papers that my group has written that I feel pretty okay about, and papers that other groups have written that I feel even better about, and see the shifts in the analysis, I think our systematic error budget is a bit underestimated currently in weak lensing, but we are not strongly systematics dominating. I was really excited seeing the HSC papers by these folks and Urosh. And so you correctly point out that your S8 is now in line with the CMB, but I was intrigued by the low omega matter. So I asked Sunao Sugiyama to make these plots, and you can see that there is a 2 sigma tension in omega matter. The Urosh pointed out that at 95% confidence, the error bars are not symmetric, so it's certainly not more than 2 sigma. When you're comparing with the CMB, I still like sigmoid omega matter because, this is the thing that CMB measures, and you can see it's still measuring it very well compared to low redshift surveys. And so this is the result I showed you, DS year 3, 2 plus 3 point. This is the HSC result, and they're both at the pure sigma level of tension. I'll make a side comment. I don't know how these guys got such good precision out of a 400 square degree survey. Slightly better than our 4,000 square degree survey. It's mostly the Subaru telescope, not them being super smart. With the beauty of the Subaru telescope, you get, three times the number density of galaxies. You go to higher redshift. And so that's the deliberate trade-off they made of going for depth rather than area. And so it's still a large factor to me, the fact that that could overcome a factor of 10 in area, but I'm sure the analysis is correct. So anyway, this is a big step forward. Photo-Z's were probably the biggest worry for most weak lensing folks, and for HSC, you've solved it. So that's amazing. I don't have much more to say about the S8 sigmoid tension. It never really was a statistically significant thing. And some people find it's almost gone to 0. Some people find it's still at about 2 sigma.
Isn't the fact that LSST is going to be in the south where you won't get the spectroscopic calibration just going to bring this issue back to light and make it even worse?
Absolutely. But isn't DESI going to get more spectra? Overlapping with LSST?
I don't know how large the.
4,000 square degrees.
8,000.
8,000.
Okay.
That's going to help a lot. But because of LSST, Roman and Euclid are also in the south. So we really better get spectra in the south. Yeah, the space surveys, for Euclid, it was a necessity to get Photo-Z's. And for Roman, it made total sense to overlap with LSST, so we will. But that means everybody's in the south.
There's the foremost spectroscopic survey, but it's not as deep
Okay.
and it's still in progress to fill in the southern regions for spectroscopy.
Yeah. Because Roman has many competing interests and not a lot of time compared to LSST, but its field coverage is still not entirely baked. And if you wanted to spend a little more time agonizing, then this is S8, sigma 8, intrinsic alignment amplitude of our 2 and 3-point function. And these are your results in this page. So you can see that maybe there's an A1 thing that's related to your higher S8. You find A1 at 1 sigma, and we find it sitting pretty much on 0. Things to agonize over. I'm guessing you've heard talks about scattering transforms from C-How, but this is my other favorite higher order statistic. Just a personal thing. There are people writing great papers with peaks and Minkowski functionals and other things, but I really like wavelet-based statistics because they have these band diagonal covariance matrices. This is the two scattering transforms. This is a second order wavelet-based harmonic statistic. And they have some really nice properties. So if you've seen the Euclid higher order statistics group's papers, they have a lot of great people, and their paper shows you how you can go absolutely crazy if you let everybody do their own thing. They have more than 10 higher order statistics, and they've spent so much time working each of them out that they don't yet have a systematics analysis of any of them. I'm sure they will. It's a great team. But Sunal started to think about, well, can we do something a little bit sane? And so this is a kind of Fisher level thing where he does all permutations and combinations of these higher order statistics. And so you can get to the same point using these different trajectories. Here he has chosen a different higher order statistic, and then this is his recommended path. So to the 2-point function, he would add scattering transform 2 for a DES-like survey, and then scattering transform 1. His 3-point function is not a complete one because you don't use all triangle configurations. So he's slightly underselling 3. So he would do it in this order. It's hope for sanity. You still have to work out a fair bit of detail, and you need quite a bit of simulations. But that's one way to select a set of higher order statistics. But there's always other considerations.
Is this path sort of constant? If you change the survey that you're looking at, do you expect it to also, that's the golden path to take? Or
we haven't worked that all out, and we are limited a little bit by the simulations we have available. So we're going to use shortcuts using the methods that I'm going to show next. Okay. I like to do things that don't involve posterior plots on parameter spaces on a semi-regular basis for my own sanity. So we learned a bit about diffusion models. As you know, diffusion models is one of the most beautiful and magical parts of deep learning, where you learn how to go from an image to your noise in many steps, and that discrete stochastic differential equation can be reversed, and you can regenerate the image not only of this dog, but if your training sample is big enough, entirely new dogs. So we are doing entirely new cosmologies. So if you just focus, these are 3 different redshift bins, but if you focus on the middle panel, then you'll see that how a trained model goes from a completely random kappa field. We're showing like 50 out of 1,000 steps to try to reconstruct this underlying field.
Sorry, I'm not sure what I'm seeing here.
So, it's just a cute animation if you enjoy that sort of thing, but just as a diffusion model, like when you write a caption, give me a picture of a dog sitting on my head and sipping a espresso, then it takes that caption, starts with a white noise field, and it uses all these steps that it's been trained on to generate that image. And so we trained a diffusion model to generate
Yeah, I
gas
think
maps.
that's the bottom row, but what is shown in the top row? You just said 3 different redshift bins, but it looks almost identical.
Yes, because they're highly correlated. The signal, the lensing mass, sorry, these are the source kappas, which are seeing mostly the same lensing mass.
Okay.
Actually, that is an important point to keep in mind. So the bottom line is that we are able to use this. So we can use it to generate new maps at less than 1% the cost of running simulations. Nice. But Supranta Barua figured out that under an approximation, you can also use it to reconstruct the truth. So this is the true kappa, and this is the reconstructed kappa from noisy shear data. So we have an analytical model of shape noise, and using that, you can do this reconstruction. And you can do it 1,000 times and generate many samples, which gets you uncertainty estimates. You can take the mean to get the things that are totally reliable, and you can compare this mean to chi-squares and see that you've gained a factor of 4.5 in resolution. I was quite excited and surprised by this factor. It doesn't come for free. It relies on the fact that structure in the universe is not a bunch of billiard balls. It's not a bunch of point masses on a grid. It's this filamentary stochastic large-scale structure. So the diffusion model is taking educated guesses based on the training data. So this reconstructed map relies on the training data. But it's only used the relationship between noisy shear and kappa. And so I learned from Olivier Doré, they independently had this idea, and they're, I think, doing something even cooler, like 3D mass reconstruction with Katie Bauman at Caltech. They have checked its dependence on cosmology, and it's pretty robust to variations in dark energy. You could imagine that if you have hot dark matter, it's going to fail. For baryons, you need to train it on hydrosims. But for now, we are exploiting this factor of 4 we've gained to do studies of comparing mass to light and so on. The other thing it uses, to your point, is that when you do chi-squares on a redshift bin, it doesn't use any information on other redshift bins, whereas the diffusion model has learned that they're highly correlated. So it kind of beats down the shape noise simultaneously. So far, it's almost certainly not suitable for cosmology analysis, but sorry, this is just a validation on scattering transforms. It works really well after we did a trick to go from the red dash to the solid blue line that you can't see because it generally agrees with the simulation measurements really well. So we checked it with many higher order statistics. And now we are starting to apply it to data. So this is our map compared to the standard Wiener filtered map for DESE, a 3 or 10 by 10 degree patch. And these are red mapper clusters. And the size has is the richness weighted by the lens efficiency.
So what is this trick to be able to reconstruct this, use diffusion to reconstruct? What is the extra part of the diffusion model? So the diffusion model allows you to, okay, but now you want to reconstruct the truth. What's going on?
Maybe we can talk about it later. It takes a little time.
Is what's going on here that the generative model is just sort of doing an educated guess of filling in the modes correctly, given what the Wiener filter reconstruction gives you?
How do you mean, given what the, it's an alternative to the Wiener filter?
Right, but so for, what the physical information is telling me through a linear reconstruction method is basically this Wiener filtered approach, where the small scales, I don't know what's going on. But then the diffusion model has learned from many, many, many simulations that conditioned on a set of large scale modes, this is the allowed space of small scale modes that my training set gives me.
Yes.
And then what's
phase
going on here is
correlation.
it's just sampling from, constrained to this knowledge.
Exactly. Yeah. So if you wanted to know how thick are, filaments as proved by weak lensing, Kaiser's it's, very hard to get a handle on that.
Okay.
How elongated are voids or, cluster halos, how misaligned are they relative to filaments in the dark matter? You can answer those questions much better. You can agonize a little bit about the bias from the training sample, but I think for these kind of questions, you're pretty solid unless dark matter is something completely different. So you can see that, first of all, clusters are not highly correlated with dark matter maps, but in some cases you can see that whereas previously it was sitting on some general supercluster area, now you can see the particular yellow dots that correspond to the cluster. Great, yes. Let me just skip this part and wrap up. So in case you're curious about these things, we've also played with convolutional neural nets as a field level inference approach. And we built our own little lightweight CNN that has special regularization methods for cosmology. And we are starting to work on interpretability of deep learning, but I'm far from satisfied with what we've achieved so far. I'm working with two great computer scientists who are applying their method to radiology images and linguistics text, and it's a better match for those, but for cosmology, we still have more work to do. And we've also, we're about to put out a paper on vision transformers that's in the NeurIPS workshop. All right. So 3-point correlations and wavelet-based statistics are powerful. We have a path to selecting a realistic set of them. Diffusion models can reconstruct mass maps and allow you to compare mass and SZ and starlight in a small-scale regime that is inaccessible so far. And there's all kinds of algorithmic advances that are necessary and happening, but modeling of systematics remains the big challenge for stage 4 surveys. Thank you.
Questions? Okay, thanks everyone. Can I ask about the diffusion? I wonder if your simulation prior to conditional on cosmology or do you fix cosmology?
We have, it's just a LCDM parameter space.
So basically you marginalize, you train on all of them.
Yes. But like I said, Olivia tells me that they've tried other cosmology, like they tested it on cosmologies that had not seen, and it worked essentially as well. But the cosmologies were only tweaking, their dark energy models. So they were not actually changing directly the small scale clustering.
And in the plot, you show this comparison between scattering, the scattering transform between simulations. And yeah, I just wonder what is the rescaling?
This is downweighting the earlier training epochs. It's like typical deep learning ad hoc trick that he somehow had the idea to try, like it was overfitting. Yeah. The questions?
was curious why you said it's better for radiology and linguistics than cosmology.
No, I mean that in cosmology, like they have a really nice method where they segment the whole image into a sum of parts, and then they have what they call a faithful, it's faithful to the performance. So it's definitely better than standard methods like saliency maps. But in the radiology images, they find a feature. This is responsible for the diagnosis. Or the other thing, these days when surgeons do surgery, when they do these arthroscopic, what is it? Anyway, one of these surgeries where you go layer by layer, and there's an AI model that colors the image the surgeon is seeing, green, yellow, red. So the AI model trained on previous surgeries makes recommendations, and the surgeons are free to override them, and some of them do, and most of the time they're wrong. The AI model is actually better than the surgeons in real-time situations like that. But why did it make that recommendation? So the interpretability metric tells you that in that MRI scan, there was this thing in the gallbladder that led it to draw this red region. You see what I mean? So it's like a individual feature to individual feature matching. Our business is a stochastic field. So yes, it tells us that these cluster-like, so like for example, 10% of the image gives you 90% of the performance. Not shocking to people who work on cluster cosmology. And then you can ask it, okay, now segment only the underdense regions. And it tells you that their omega matter is a little more sensitive to the underdense region. So we have some things, but we have to come up with some more precise questions. Yeah.
Okay, I'll ask another one. I wonder in this, like you have this path where you like how to combine different high order statistics, like which one gives you more information. Like in that plot, I noticed that you firstly add in the second order scattering transform, and then in the end add the first order. But presumably the second order gives like there are much more coefficients, right? So I just wonder like. If you compare, for example, the information content per dimension, how would that?
We don't do that. Yeah, this is just asking the question in the way these higher order statistics are used. So like in that plot, ST1 wouldn't do badly by itself. Right, the first order scattering transform would probably be somewhere here by itself. But as an increment to everything that came before it, it's only a modest gain. So, yeah. It's going to take a fair bit of work to make this useful, independent of survey properties and so on. But I do like Sunar's idea.
Okay, so let's thank you again.